So my project's going to be on flash drive and a USB port. That'll be the system I'm studying. And just as a background, here's the system in the picture. It's a flash drive with a lanyard attached. And the reason I think this is very relevant to study is because at universities everywhere, people are using lanyards and people are also using flash drives. And you might have a flash drive attached to the end of your lanyard, and you just plug it into your computer without a second thought. And so it's important to understand because lanyards often just don't just have USB drives attached to them. They also could have keychains and other things attached, and that'll just increase the amount of force you're going to be putting on the flash drive when you plug it in. And so it'd be very relevant to understand how much force it can take, as well as the amount of deflection it can that you want it to have. That maybe if it goes beyond that, it starts doing damage, and with damage might come loss of information. So yeah, this is the system that we're going to be studying, and it's basically a basic cantilever system, and we're going to pretend or model the laptop as being fixed. There's going to be that lanyard uh, expressed as that external force P, and there will also be a momentum going down. And so in the analysis of the system, stuff that would be good to analyze would be the maximum allowed deflection, which I'm saying is 1 millimeter, the maximum allowable force they should be putting on that for that p-value, which initially I'm going to say is 4.4 newtons. Shear and bending moment diagrams, shear stress, and deflection. So now we have our, excuse me, we have our deflection analysis. If I could move this real quick. As I was saying, now we have our deflection analysis. And so it is modeled as a cantilever beam under transverse loading because our applied force is acting perpendicular to our beam. And if we look at the model that we have over there on the right, we can see that in order to solve for the maximum allowed deflection or for any deflection that occurs, we need to model it as a cantilever beam and follow through with the equations that I have listed there as it's sort of worked out. We end up at the bottom with YA equal to negative PL cubed over 3EI. So that is going to be our equation to solve for deflection or define what the deflection is going to be. Now we just got to fill out what the variables are. So P, which is our applied force, would be 4.4 newtons. 4.4 newtons approximately pound force. So I figured that'd be a good place to start, just to test as a test value. And then our E would be 2.3 GPa, which was found online. And then our moment of inertia would be 703 millimeters to the fourth power. And then our length would be 57 millimeters. And so as you plug the numbers in and adjust for units, you get a deflection of 0.167 millimeters. So that is way under the 1 millimeter maximum allowable bending that we had. So if we want to work to that boundary mark or constraint, we have to have our YA be 1 millimeter. That way we can now solve for the maximum allowable force that we can apply to it. And so once we make that change, we see that the maximum allowable force that we can have as the maximum force that our keychain can apply onto this USB drive would be 8.73 newtons. So it'd be important to remember that in the system, not to exceed that. So now we can move on to the shear bending moment diagrams. And here it is modeled with P being 4.4 newtons. You can do your sum of the forces equals 0, and then you can solve for what those values are. So since we just have a fixed end and an applied force at the end where P is, it's 4.4 newtons, which would be the shear force, and then it drops back down to 0 as you hit the fixed point. And then below that we have our bending moment diagram. And since the shear force is negative, our bending moment diagram slope is also going to be doing negative like that, or going underneath the axis, because it's maxed out where the fixed point is, and 0 at the free end because it's not fixed there. But the way to solve for it would be 4.4, which is the applied force, times 0.057 meters, which is the length of the USB drive, and we get the max bending moment of 0.2508 newtons per meter. But that's just a test value. So we found out that the actual max shear and the max bending moment can be found with P equal to 8.73. So the max shear force would be 8.73 newtons, and the max bending moment would then be 0.4976 newton meters. So with our shear stress, you can see that we still have the same sort of free body diagram to use, cantilever system. So we use our shear stress equation, which is T max is equal to VQ over IT. And we have below that free body diagram, we have an image of what the face looks like when you look at it on the side along the axis, the length of the USB drive. So you can see the dimensions there. And to start off with, we once again go with our initial guess, which was if the force is equal to 4.4 newtons. And so we use the T max formula, the tau max formula. We use some of the forces along the v direction to be zero, so v would be 4.4 newtons. If we're going to solve for q, we have to use the area times the length of that centroid. So since we're solving for the max shear, we actually use the neutral axis. And so the neutral axis is located 7.5 divided by 2 millimeters from the top. But for the centroid distance that we're looking for, we need it from that neutral axis to the centroid between the neutral axis and the top. So in order to get that, we have to do 7.5 divided by 2 minus 7.5 divided by 2 times 1.5. And so once we solve for all of it, we get Q equal to 140.65 millimeter cubed. Then we do our moment of inertia. So we do 20 times 7.5 cubed divided by 12. We get 703 millimeters to the fourth power. T is just a thickness, which is 20 millimeters. And so once you put it into the tau max equation, we get the max shear is equal to 0.044 megapascals. But as I repeat again, we have to do it for P equal to 8.73 newtons. And so once you run it back, you get that the max shear is actually 0.0873 megapascal. So those are the boundary conditions that we're going to be working with. So if we want to just review quickly what our max conditions are, max shear would be 0.073 megapascals. If we go back, the max shear is 8.73 newtons, max bending moment is 0.4976 newton meters. And then the maximum allowable force that we have is 8.73 newtons because that's what causes the maximum allowable deflection, which is 1 millimeter. So that is my final project for mechanics of materials. Thank you.